So now I can
Like, I was like really confused on
yeah. It's like let's wait for a second.
except it's like down, like this is like half or whatever. And they said that it was like big one big so that would lie that bit. So I was like, yeah, it's like this is always
I know that. If I reset
Okay, so let's get started. This is the last section in chapter 14, and it's basically on principle of conservation of energy. Okay, so last time we talked about principle of work energy, and this is the counterpart. This is another principle, and I'll tell you when to use which principle after we define a few things. So first of all, conservative forces are forces in which the work done is independent of the path taken. So examples are gravity. So if you move an object from here to here, You can move it this way, you can move it this way, this way. What matters is the final and initial position, and that determines the potential or the work done, right? mg y2 minus y1. It doesn't depend on the path taken. So those forces are called conservative forces. Another example is spring. The energy depends, the work done depends on the initial and the final position. It doesn't depend on how you stretch it, how fast you stretch it, or how slow you stretch it. Non-conservative forces are forces in which the work done depends on the path taken. So example is friction. If you move an object from point A to point B, you move it in a zigzag fashion, it's going to be a different work compared to moving in a straight fashion because the work done depends on the path taken. Right? So the principle of conservation of energy is to be used only when you have conservative forces. And in this course, we are only talking about two conservative forces, gravity and spring. So if you see a problem with spring and gravity, you want to use principle of conservation of energy and solve the problem. If there are non-conservative forces like friction, and the other one is external force or moment, then you want to choose a principle of work energy, which we did last class. Okay, and this will become clear as we solve more problems. Okay, so in this equation which I've described, T1 and T2 are the kinetic energies. We've seen what those are, but we've not seen what the potential energy is. So I'm going to define the potential energy of the conservative forces, in this case springs and gravity. And then we should just use that to solve problems. Let me define potential energy terms, which is denoted by V. Okay, the first one, and there are really just two things we are concerned here, that due to gravity and that due to spring. So first one is gravity potential energy, and we will use the notation Vg. So when you solve problems involving potential, I'm sure you've heard of this in a first class, like a physics class, where you have to always look at potential with respect to a datum. Okay. So if you are on the datum, then the potential is 0. If you are below the datum by a distance of phi, then your potential is negative, and if you're above the datum, your potential is positive, where you just write mgy and mg, where m is mass, g is gravity, and y is the height from the datum. The second thing is the elastic potential energy, which I will denote by VE. And VE is always positive. It doesn't matter if you stretch the spring or you compress the spring. It's always half Ks square. Okay, let's see potential and compare it with what we had for the work done. So if you go back to the note size for the last class, when we looked at the work done of a particle, we said if the particle moves down, then mgy is mg force is down, the displacement is down. You take the product, the work done is positive. However, the potential is negative. Okay. Similarly, when you move an object up, the force is mg is downwards, the movement is upwards. So again, the sign is negative, but the potential is positive. So remember that you switch signs when it comes to gravity potential. It doesn't have the same sign as work done. For elastic potential, if you compare it with work done due to a spring, we saw that the work done by a spring is negative no matter what, but the potential is positive. Okay, so everything here is switched signs with work done, which I think leads to a big confusion. Now, when you're solving problems, you have to remember this. What I do is I do not try to remember there are two expressions for work done, for gravity and potential, and two expressions for potential, right? I just remember one of those two. So, for example, I will remember, usually I like to remember potential. So I remember this picture, but for work done, I just switch the signs. So it's up to you how you want to remember it, but I would recommend remembering only one of these, and the other one is just change the sign. Okay? If you do not use the right sign, you will get the wrong answer. So it's very important that you stick to the sign convention. Okay, so let's see how to use these principles by solving some problems. So if the 20 kg cylinder is released from rest at h equals 0, so you can see this is h, which means that initially the cylinder is here, the spring is attached this way, and it's at rest, so velocity is 0. Determine the stiffness K required of each spring so that its motion is arrested or stops when h equals 0.5. Each spring has an unstretched length of 1 meter. Okay, so what's going on is you set the system up so that the block is in line with the two pin joints, and then you release it, and obviously it's going to bump around, but it's eventually going to stop at height h. You're going to find that height h. No, sorry, you're given height h, you're going to solve for k. So first of all, for this problem there is only gravity and there's a spring. So we can use principle of conservation of energy to solve this. Okay, so use principle conservation of energy. Okay, so T1 plus V1 equals T2 plus V2. T1 is the potential when it is horizontal. When the system is horizontal, it's clearly 0. Starts from rest. It turns out also ends up with rest. So T2, final kinetic energy is 0. Okay, let's write the initial potential energy. Now, this thing moves under gravity and due to the effect of a spring. So we need to account for both those potentials. So this is given by two terms, VE, the spring energy in position 1, and VG1. Okay, VE1 is the energy of each of those two springs. For that, I need to do, first of all, what I notice is that both those springs are stretched or unstretched equally. So I'll just find the energy of one spring and then just multiply it by 2. So 2 times the energy, half K, and the definition for energy is that's half K times the stretch squared. So what is the stretch in the spring? It's 1 because the initial length is 2, the unstretched length is 1, it's given here, squared. This is also a common mistake people make, which is they do not account for the stretch, initial stretch. Half K S stretch, S unstretched. Okay, and then to find the potential energy due to gravity, if you remember the notes I put down there, you need to define a datum, otherwise you cannot find the potential energy. So we can fix the datum anywhere you want, really. It doesn't really matter. Any of those lines would do, right? But to make your life easy, I would recommend choosing datums either at the first position, the horizontal where it starts, or the final position where it ends, because that way one of the potentials will become 0. So for example, let's say that we put the datum here. Okay, what that does is it makes the initial potential 0. So that's V1. V2 is VE1, VE2 plus VG2. So again, the potential due to springs is going to be twice of the energy of one spring, so half K. Stretch, so we need to find the length of the spring when it is stretched. That's going to be, well, from Pythagoras theorem, it's 2 square plus, since h is 0.5, this length is going to be 2 square, which is this, plus 0.5 square. So 2 square plus 0.5 square. Minus the unstretched length. Don't forget about that. That's still 1. It's a property of the spring. And this whole thing should be squared. Plus the potential due to gravity. Okay, so mass times gravity times the displacement from the datum, which is h, or 0.5. And then we need to put the sign. So if an object goes below the datum, and the potential is negative, so I need to put a negative sign here. Okay, so all these things go in the equation. Zero plus K2 minus 1 square plus, so equals K times minus 29.81 and 0.5. That's clearly a single equation in a single unknown, and you can solve for K. Any questions on that? It's very straightforward. Once you identify it's to be solved using principle of conservation of energy, everything else flows. Any questions? Okay. So one of the sort of the famous problems in this category is a pendulum falling under gravity. Okay, here is one. The ball has a weight of 15 pounds and is fixed to a rod having a negligible mass. So this rod is massless, if it is released from rest when theta equals 0, which means this is the initial condition. Determine the angle theta at which the compressive force in the rod becomes 0. So the compressive force becomes 0, or the tension in the rod becomes 0. Okay, so first of all, when you're asked to find a force, the first thing you want to do is draw a free body diagram, because you cannot write an equation for the force unless you have a free body diagram. So let's draw a free body diagram for the pendulum. When it is at an angle theta. So mg so this is not a string, it is basically a rod, which means that the force is not going to be in this direction. It has to be in the upward direction, otherwise it don't make sense to have the force in towards the center of the rod, or towards the pin joint. So when things are going in circles, you have the option of choosing polar coordinates or anti-coordinates. They actually essentially are the same coordinates for things going in circles. So let's just choose anti, but it can totally be written in terms of r theta. I'll give you the same answer. So draw the coordinate frame. N always points towards the center of the circle, and ut is in the direction in which the ball moves. Okay, so we have that. Let's write the equation of motion, because we're trying to find the normal force. This angle is theta, so n with a negative sign, because n is in the negative un direction. Mg cosine theta is the force acting in the un direction with a positive sign, equals the mass times the acceleration in the normal direction. So mass times v, let's say that the velocity here is v1, velocity here is v2, that's when the normal force goes to 0. V squared divided by the length, let's call this the length. Okay, so you're asked to find n becomes 0. N becomes 0 when mg cosine theta equals mv2 square divided by L, or cosine theta equals v2 square divided by g times L. So theta is the unknown, you got to find theta. L is known, g is known, but v2, that's the velocity in this position, is unknown. Okay, and you cannot write this answer as it is, because v2, you got to give a value for cosine theta in terms of something which is known. So clearly this doesn't solve it. So the question is, can we find v2? If we can find v2, then we can sub that in that equation and then solve for theta. So we'll try to solve for v2. Okay, so this is where we can invoke the principle of conservation of energy, because the only forces acting in the system are gravity forces, and gravity forces are conservative forces. So principle of conservation of energy, this is to find v2. So T1 plus V1 equals T2 plus V2. Okay, the pendulum starts with a 0 speed, so T1 is 0. There's no spring, there's only gravity, so we need to find potential due to gravity, but potential due to gravity can only be found if you have a datum. So you got to choose a datum. Now, as I said, you have two choices. Well, you have lots of choices, but two choices make sense. One is putting the datum right at the initial position, or put the datum right at the final position. Okay, both those will give you the same answer. So initially for the previous problem, I put the datum at the initial position. This time I put it at the final position just to show you that it also works. So let's put the datum here. Okay, it's up to you where you want to put it, but both those will give you the same answer. So put the datum there. Now we ask ourselves, what's the potential, initial potential? It's going to be mg times this distance. Okay, we can find this distance by noting that this length is L cosine theta, right? If this is length L, then the vertical is going to be the component of L in the, and you need to use cosine. But we also know that the length of the pendulum is L. So this distance, which is the unknown, x or y if you like, is going to be L minus L cosine theta. Can you see it? L is the length of the pendulum minus this distance, L cosine theta. So L minus L cosine theta. Since the bob is above the datum, the potential is positive. So positive sign stays. Equals the final kinetic energy, which is half mv2 square, plus what's the potential at 2? It's 0 because the datum is at 2. Okay, so we can solve for v2. It's simply 2gl. Let me solve for v2 square. It's 2gl1 minus cosine theta. Okay, so I got an expression for the velocity at position 2. I also have another expression for velocity at 2 from 1. So I can put 1 in 2 or 2 in 1, whatever you like, to get cosine theta equals 2gl1 minus cosine theta divided by g times L. So if you solve this, you get cosine theta equals 2/3 and theta equals the inverse of that, so it's 48.2 degrees. So it's very interesting that the final answer does not depend on mass, it doesn't depend on gravity, it doesn't depend on the length. It's the same no matter what the length is, what the mass is. This is actually a classical result in dynamics, that angle is independent of the features of the pendulum. By that I mean the mass, gravity, and the length. Questions? Yeah.
We have force F. How come we were able to solve the principle?
Well, we use equations of motion for. Why? How can we use the principle? Yeah, okay, good. That's a good question. I actually ignored that in my. So N is acting through the pin joint. So it doesn't really have any potential. It's not going to. We can think of potentials as something which can have the ability to do work, because when you move a mass up, it has ability to work. Same for the spring. When you stretch it, it has the ability to work. When the force N acts, it's passing through O, so it's going to do no work, and consequently, it has no potential. So you can ignore as long as that force has no potential to do any work. But this can also be approached by considering principle of work energy, in which case the work done by mg is there, and there's no work done by n because it acts through the pin joint. That's a very good question. I sort of ignored that. Okay, anything else? Yeah.
Why couldn't it be, why is it that angle? Anytime it passes the 90 degree, it would be in tension, and then compression would be 0. So could there be more than one answer?
Okay, so what happens when theta is 90 degrees?
Because then there would be no force acting on the rod in that direction. That was just me conceptually thinking about it there.
So I think when theta is equal, so you think what happens when theta is 90?
Yeah, anything past 90, because then it would be pulling and it being.
Yeah, so when it goes past 90, the end reverses direction, for sure. At theta equals 90, I think there is a force mv square divided by r acting this way, and then mg is acting that way. So the force will not be 0 when theta is 90, because there's one force mg that way, downwards, and there's force due to centripetal acceleration mv squared divided by r. Can there be two answers? Well, it turns out that if you start the system from the top position and if the force end disappears, then it's going to be in free flight. So there is no second answer because you're going to look at the first answer. So once you lose contact, then things are going to be sort of, in this case, things are not going to be crazy because that it's a rod and so it's still going to maintain that length. But in this case, yes, the cosine inverse is 2/3, has more than one answer, right? Cosine is positive in the first quadrant, and I think first and fourth quadrant. So it is actually the two answers to this problem are theta is 48 and theta is minus 48. So saying that you go this way or this way, which is the symmetric solution. Okay, so here's another pendulum problem. Want you to do it. The 2 kg pendulum is released from rest when it is at A. So it's released from here. Determine the speed of the bob and tension in the cord when the bob passes through the lowest position B. So I would like you to solve only for one part. You don't have to solve for the speed. Okay. Let's draw a free body diagram. Tension, well, mg, and then you can use un ut because in this case it is moving in circles. So t plus t, because it's acting in the un direction, minus mg equals mv. Let's call this instant 2. This is instant 1. v2 squared divided by the length, which is this. So you got to answer for the tension. It should be a numeric value. You know the mass, you know gravity, you know the length, you do not know velocity. So what you want to do is solve for velocity using conservation of energy, plug it in that equation to solve for tension. So I want you to pull the answer for tension, but first you need to solve for V2 first. And then you got to pull the answer for T. Okay, so use conservation of energy to find V2 first. Yeah, please. Absolutely, yeah. You can use what I just taught. That's why it equals T2 plus V2. I wrote down the final kinetic initial. I just have to write the initial and final potential. Let's choose, so the previous problem I choose the datum right below. Let me choose the datum right here on top, just to show you that you can also do it this way. Okay, if you choose the datum right on top, then the initial potential is going to be 0. The final potential is going to be mg, so that's the potential at B, times the distance. It's going to be the length of the pendulum, and since it's below the datum, it's going to have a negative sign. So V2 equals GL, so V2 squared equals 2GL, that's what you get. I would put this over here and solve for T. So T equals mg plus m, V2 squared is 2GL, so it is 3mg, which is 3 times 2 times 9.81, which is 6 times 9.81, 58.86. Okay. Looks like that's what. I'll set up this problem and then complete it later on. You guys will leave early? Should I set it up or? Okay, so let me set up the problem and then complete it. When the 5 kg box reaches point A, so the box is moving to the left. Velocity at A is 10 meters per second. Determine the normal force the box exerts on the surface when it reaches point B. Neglect the friction and size of the ball. So this is very much in the flavor of the pendulum problem I did, where the force is asked. So draw free body diagram of the particle at point B. Normal force mg, and there's no friction, so that's about it. So in this case, since you're given the movement you're given the coordinates of the curve in x, y, I would only recommend using NT coordinates. Do not use anything else. So UN, UT, and then there's another thing here. I want to eventually find the angle. So let's call this theta. Let me it's easier to have called this theta. So this is theta, because you can see that's actually 45 degrees. Because the angle made by y equals x, it's 45. Okay, let's set up the equation of motion. EOM n minus mg cosine theta. N is positive because along UN, mg cosine is negative because along negative UN, equals mv b square divided by rho. In this case, rho is something I need to find. Okay, so n is unknown. Theta is known. I just found it's 45 degrees. VB is unknown. I can find rho because there's a complicated formula dy 1 plus dy dx squared and so on. So the only thing unknown is VB. To order to find VB, I need to use conservation of energy. So T, in this case, I'm going to use A and B because A is the initial point, B is the final point. TA plus VA equals TB plus VB. Initial kinetic energy is half mVA square. VA is given. For the potential, there's only gravity. So I can choose the datum the way I want. Let me choose the datum to be right here. So let me set this up and I'll let you go, okay? VA is going to be 0 because on the datum, the kinetic energy at B is VB square plus potential is mass times gravity times the height of VB, so VYB. And since it's above the datum, it's going to be positive, so its sign is fine. So VB is unknown here. YB is also unknown, but you can find YB because it's the intersection of the curves y equals x and x raised to half plus y raised to half equals 3. So let me finish this up and post it, but the key message is that when you have only gravity and springs, use conservation of energy. So a quick announcement.